All right, let's get started. Thank you all for coming. My name is Shrikant Kandula. I'm from Microsoft. I'm going to tell you about multi-resource packing of tasks and cluster schedulers. This is joint work with Arun and several others at Microsoft. If there's one thing I want you to take away from this talk, it is that being aware of the resources that you're scheduling and being a little bit clever improves both the service latency objectives and the return per dollar for your investment. So here's the problem. There are jobs, set of jobs with tasks and dependencies on one end and set of resources, machines with a network on the other end. And in the middle, you have these cluster schedulers such as Yarn that are trying to match tasks to resources. So this is the core problem that we're going to consider in this talk. So the objectives in doing this are that you want high cluster utilization, you want jobs to complete as quickly as they can, and you want predictable performance or some fairness guarantees if you have multiple people sharing the cluster. So why is this hard? What makes this interesting? Some reasons are that the tasks that you're trying to schedule can have very different durations. You can have something that lasts from less than a second to something that can last maybe an hour or even longer. Tasks have very different, use different amounts of resources. Most mappers are not network heavy if you get locality right. But almost every reducer is network heavy because it is pulling from a lot of other locations. What's complicating in frameworks that are not just MapReduce or not just Hadoop are dependencies between tasks. So you cannot, these are data dependencies. You have to get to your input tasks to finish before you can run these later tasks. So what's the effect of this? Let me give you a few concrete examples. The first one I'm going to talk about is fragmentation. Suppose you have a single resource that you're worrying about, just the memory, and you have 3 tasks. 2 of them require 2 gigabytes of memory, one requires 4 gigabytes, and your machine capacity is 4 gigabytes. If you just randomly allocate them, it's very likely that you'd end up with an allocation that looks like what's up there. Both machines have 2 gigabytes free, and you can't put your third task in. You must already be thinking about how you can do this better. This is the traditional problem of fragmentation. And the fix for fragmentation is what's called packing. In this case, if you pack properly, you can get up to a 50% increase in your task throughput. Let's look at the converse of this problem. Hadoop and other schedulers are not very careful about allocating the network usage and the disk usage to tasks. Suppose you have now the same set of tasks, they all still use 2 gigabytes of memory, but say they both use the entirety of the network bandwidth. If you only looked at the memory and allocated tasks, both these tasks would look really nice. They do fit in the memory, so you would go ahead and allocate them. However, what happens is that the demand on the network is twice now as much as capacity. So these tasks are going to just wait and be slowed down because they're both competing with each other on the network. Instead, if you had a third task that does not use the network, let's call that T3, just uses the memory, instead of putting a network intensive request along with the other network intensive request, you could fill the spare memory with a memory intensive request. In this case, by avoiding over allocation, you could still get your 2 tasks per T throughput, whereas if you did over allocate, everybody was slowing down and your throughput falls down by up to 100%. Clearly, these are a little bit of an extremum examples, but you get the point. I'm going to show you examples where these are not just MapReduce tasks, but there's dependencies, and not looking at packing carefully makes your problem much worse. Here's a DAG. The tasks in the blue have long durations. Imagine them to take some capital T time, and they have a small resource request. So the label there is duration and resource demands. The tasks in red are small duration, but they have fat resource requirements. So what would critical path do with a DAG like this? Critical path would look at which of the tasks has the longest critical path and schedule them. So in this case, the one on the extreme left has the longest critical path, and then the one on the it goes from left to right, basically. So you get a schedule that looks like this one. Every time you run a blue, and then you run the red, because the red and the blue don't run together, and then you go to the next blue. You must already be thinking about how to do this better. You can indeed get all the reds scheduled, because they have no dependencies among them, and then overlap all the blues at the same time. So in this example, critical path scheduling is n times worse than the optimal schedule. The reason critical path is this bad is because it's ignoring resource demands. It's only looking at the duration and the length of the critical path, and it's not looking at packing. And for things with dependencies, if you just looked at a packer, it can't look at future packability. A greedy packer that only looks at current packability can also be d times worse if you have d resources. All right, so we have heuristic solutions to this problem. Before I get into the solution, I'm going to tell you about the architecture. You must be familiar with everything that's currently on the slide. On the left are application masters. There could be different ones. And on the right is the cluster. In the middle is the resource manager. So what we do is we extend these application masters with what we call schedule constructors. You should think of them as a soft hint as to which of that job's tasks should run before the other tasks. And the resource manager then is extended to also do packing along multiple dimensions and do that with bounded unfairness. It enforces the schedules that the AMs are asking, and we also have an overbooking logic. We also extend the heartbeat mechanisms in order to plumb the requisite information to get this all working. So one slide overview of the multi-resource packing. If you think a little bit, this is a bin packing problem. You can think of each task as a multi-dimensional bin, CPU, memory, network, and disk, and each machine as a bigger multi-resource bin into which these balls are falling in. Packing then is really just packing. You want to make sure that more balls fit in each bin. This is a very hard problem. In fact, it's NP hard to get a constant factor approximation. So here's a heuristic. We look at the resource demand vector of the task. Let's call that D, and the machine available resource vector R. If the task fits in the machine, D less than R, we compute an alignment score, which is the dot product between D and R. What this does is, if the machine has a lot of network free, then a task that actually reads the network gets a higher score, because those things will align better. In fact, if the task doesn't have any memory free, then machine has no memory free, then a task that requires memory won't even fit. So you wouldn't even overbook. So packing by itself is not a panacea. It doesn't solve all your problems. In fact, one of the problems that doesn't solve is it ignores multiple jobs. So if you have a job that has exactly one task waiting, but it so happens that that one task doesn't have a good packing score, the job will just be kept waiting all the time and it won't complete. So in addition to packing, we supplement it with this heuristic that picks jobs based on shortest remaining work. So there's a formula how we compute shortest remaining work, but the way you should think about it is all other things equal, it is better to schedule a task that's coming from a small job rather than from a big job, because it's more useful for your completion time. You must already be thinking, what about fairness? It's a multi-objective optimization that most cluster schedulers have to do. If you pick packing efficiency, I already told you can delay jobs. If you pick job completion time, you might lose out on packing because these tasks don't pack. And if you pick fairness, you might lose out on both of them. So we have implemented a mechanism that lets you effectively trade off between all three of them. And in fact, what we show is with a small amount of unfairness, the best performance you can get is close enough to the really best performance you can get. That means a little bit of unfairness gets you most of the optimal performance. And the reason to think about this is, what are we being fair over? We are being fair over multiple jobs. So But what we want for performance is packability. So as long as the different jobs have roughly similar tasks, you still get your packability while being fair. But you have to be a little bit unfair. One slide on how to deal with tasks with dependencies. Imagine a complex DAG. We pick a troublesome subset. These could be tasks that are long running, potential stragglers, hard to pack. We place these tasks first on a paper schedule, a resource time schedule. And then we pick the remaining tasks. The green are the parents of the troubled, the yellow are the children of the troubled, the O are the others. We have to break them up because you have to respect dependencies. The parents have to run before the trouble and the children after. So there's a systematic way you need to place these other tasks so that you get a feasible schedule. And then we convert this schedule to just a precedence order over the tasks. And the precedence order is just given to the resource manager at runtime. And we also at the runtime have some heuristics to overbook. We have bettered lower bounds on how well a DAG will run. And using these lower bounds, we can show that Microsoft has a big data cluster. We run DAGs in there. So on those production DAGs with real durations and resource demands of those DAGs, when we apply this logic, we get nearly optimal for 3/4 of the DAGs. The last quarter, we are far enough away from them. It could be because our lower bound is not precise enough, it is not, or it could be because our scheduler is not good enough. We are not sure which one yet. So 2 slides on results. This is the result from 20,000 DAGs in production. On the x-axis is the reduction in job duration. A value 0 means no gain. Anything to the left of 0, your left of 0 is a regression, and to the right is a gain. You can never improve by more than 100% because that would mean jobs are running at 0. The y-axis is a fraction of DAGs of the 20,000. So there are a couple lines here. The green line is a random order. That means among the runnable tasks, pick the next one to place in random and be work conserving. If you just pack the runnable tasks, you get the blue line. At median, you get roughly a 10% improvement, and about 20% of the DAGs improve by 30%. If you also are careful about dependencies, you get much higher gains, and we are closing to the lower bound. You must be wondering how these gains are coming from, so I'm going to show you a little bit more of a descriptive experiment. So what we are doing here is we took 200 jobs from TPC DS. It's a well-known benchmark. It generates SQL. It's written in SQL, but the data plants could be if you use Thales or Hive, you get a DAG out of it. The x-axis is time. The y-axis is the running tasks in the cluster. It's a 200 server yarn cluster. Again, there are a couple of lines here. The green and the orange, which are a little bit indistinguishable, are default yarn and Thales and plus critical path scheduling. Critical path scheduling really does not buy you much. If you put packing, you get the blue line, and if you do packing and dependencies, you get the red line. So what are we getting? We are getting experiments finishing faster, make span is faster, and the reason we are getting that is because we are always able to run more tasks per unit time. So higher utilization from better multi-resource packing is giving us faster make span. Let's look a little bit deeper. I'm going to show you resource utilization over time. The bottom graph is for default. I'm going to show you 4 resources, CPU, memory, disk, and network. You already see that memory, network, and disk are over-allocated. Anything above 100% is an over-allocation. And CPU and memory are not that tightly allocated. They're hovering around maybe 30% allocation with occasional spurts. You see how packing is helping. Very rarely does anything go above 100%. So we avoid over-allocation by fiat because we are asking for a fit. And even the remaining utilizations jump up a little bit. You cannot get high utilization on every resource because it depends on the task profile, which resource is tight and which time, and the jobs that you're running. So as long as some resource is tight, you really don't know how much more you could do. This is what we do when we do overbooking and dependencies. The average utilization jumps up a little bit further because we are doing complementarity between tasks, and we also do slight overbooking. Disk and network are slightly above, but not too much above. All right, so that concludes one large chunk. I'm going to hand it off now to Arun, who's going to tell you about how to get this nicely implemented.
Hi, I'm Arun. So I work with Srikanth, and I'm just going to go and give you a laydown of my adventures in trying to go and encode a bit of this into the yarn framework. So this is basically the desired scheduler logic. It's too complicated, so I'm just shortening it up a little bit for you. This is what happens when you get a node heartbeat. While a node has free resources, for each point pending task, you compute different scores, and we pick the best scoring task and assign it. So essentially, the capacity and the fast schedulers assign one task per heartbeat. I know before people who are more familiar with the capacity and fast scheduler hound on me, I understand that you do assign more than one task sometimes, and in fast scheduler you have the assign multiple, and capacity scheduler also you have while loop, but that would equate to this random curve which Srikanth actually mentioned. It is okay. So what we did essentially was this. We introduced something called a bundler API. So the goal of the bundler API essentially is to allow multiple containers to be allocated per heartbeat iteration, and a bundle, as it's written over here, it represents best possible multi-container assignment to a node. And so the actual and we introduce this concept of a deferred allocation. What this means is like during an assignment loop, what happens is you don't actually assign it. You say that you are deferring the allocation. Once you finish the iteration and you exit the loop, that is when you actually create the container and assign. So essentially, we have a bunch of different bundlers, and we have a baseline bundler that is actually replicates what the current scheduler does. What it does is it stores the first task it finds into the bundle, and it terminates the loop, saying that okay, that's enough. That's our baseline bundler. But and we have, and GoodFit is a version of the bundler that actually bundles multiple tasks. So we introduce a concept called a bundle context. So a bundle context is additional context that is available to. So before that, I mean, this goes a little bit deeper into the code. So your scheduler code hierarchy, there is an abstraction of a scheduler node called a scheduler node. So we added some additional context to this node. It's called a bundle context. So when a node heartbeat comes, the bundler API, what it does is the implementation of the bundler will try to add the task to the outstanding bundle that is associated to that particular node of the cluster. So this is the API that we kind of added, and all our bundlers implement this. So it has something called a bundle state. The bundle state is something that is checked during each iteration. I mean, if you look at the fast scheduler, you have each call of the assign multiple. In the capacity scheduler, you have a while loop that checks if you can assign more resources to the node. So the check means that yes, there is a bundling opportunity available, and the assign means that no, there is no more bundling opportunity for this particular task on this particular node. And these are the return types. So the return types is once you add a task to a node, there might be cases where you want to go and terminate the loop. So certain cases where you would want to go terminate the assignment loop is like, for example, it's a application master task. You don't want to go and assign anything more beyond the application master. And the thing is that you don't want latency while allocating an application master, obviously. So we kind of return out of the loop the minute you see an application master. And the other reasons why you would want to terminate the loop before completing the bundle is, like, for example, if you already have a reserved container, or you have relaxed locality equal to false, obviously, when you say relaxed locality equal to false means you are no more amenable to any more tips and tricks for bundling and stuff. So yeah, so essentially what we did is we did some changes. We made some changes to the capacity and the fare scheduler. So this is most of our code changes actually happen over here. You have in the capacity scheduler you have a parent queue and there is a loop called the assign container. What we do is we call that method multiple times in a loop and then we try to bundle as many tasks as you can. And once you finish the loop, we have a special commit assignment method. What it does is it will actually get the task that you assigned and then it will actually go to the parent queue and then again do the actual assignment. So these are the bunch of JIRAs that we had actually opened up for this effort, yarn 2745, yarn 4056 and specific changes. We have design talks there and I think I have one patch there, but then that's kind of 2 weeks old. It doesn't compile right now, but we are actively working on it. Yeah, so now back to Srikanth on all the stuff.
So you must be wondering, how do we get this right in practice? Estimating task demands and durations are key inputs to the scheduling decision. Hadoop already lets people specify the cores and the memory they use. In practice, they're overestimates. For network or disk and for other things, it's a little bit hard to estimate a priori based on your job and it requires expert. So what we did is we built this mechanism that uses historical information and feeds it back. So you can measure when tasks are running the peak usage of various resources and use these estimates either for tasks in later waves. Say you have a map with 1000 tasks and your cluster can only run say 30 at a time. Then after you've run 30, everything else gets the better estimates based on the previous 30. Or you could use it for recurring jobs. Again, back in Cosmos, we have a lot of recurring jobs, so also in Facebook and other clusters separately. So parts of this are done and have been checked in. They've been checked in for a while now. There's a different approach that I just wanted to bring to your attention. Several people have worked on sampling to estimate resource demands. That is, what they do is you pick a random subset of the input and try to run your whole query on that random subset. And in the process, you try to infer what the various tasks are going to use. We believe that this is not a widely applicable approach because extrapolating from what you saw in your sample to the real data is kind of imprecise. And even otherwise, if you have a deep DAG, say you have a join, then in order to get enough input for your join, you'll have to run a lot of work on both of the, on everything below the join in order to get enough data out of the join task. So we have a new approach that is targeted at estimating resource usage and duration for ad hoc jobs, jobs that you've never seen before. Because for recurring jobs, we anyway have history information to use. And we are happy to chat with you guys if you're interested. A second ongoing work that I want to tell you about is what we call temporal relaxation. Here's an example. Say you have two MapReduce jobs, identical for all purposes. Map is disk heavy and reducer is network heavy. All the mechanisms that we have implemented today, fair share, dominant resource fairness, they're all instantaneously fair. In this case, what they're going to do is you're going to run each map with 50% of the cluster. So the maps will finish at time 2t. And then you run both reducers again with 50% of the cluster, so reducers will finish again at 4t. So now both jobs are finishing at 4t. Can we do this better? So here's an idea. Forget about instantaneous fairness. Suppose you run the mapper of one of the jobs completely, like give it 100% of your 100% of the disk. But once that job gets into the reduce phase, you can overlap that job's reduce phase with the second job's map phase. And because these tasks now require different resources, you're able to run all of these tasks at the same time, complementarily. So in this case, what you've gotten is jobs are finishing at 2t and 3t instead of both finishing at 4t. So if you step back, a lot of these fairness schemes tell you that they're Pareto efficient, but here you have a scheduler, you have an example where you have a Pareto dominant answer. Every job is finishing faster than it would have in the instantaneous fair schedule. Pareto dominance means that if one of the jobs is benefiting, somebody else must be getting slowed down. In this case, that's not happening. Everybody is benefiting. So the key insight here is that if you're being instantaneously fair, because tasks can have different demands, you could have a pretty bad make span. And the way to think about this is you shouldn't be. You should, nobody really cares about nobody really cares about fairness. Nobody's really coming in and every second measuring, is this job getting half the cluster, is the other job getting half the cluster. What they probably care about is when the job is completing. So suppose we take that as the invariant. So you give as an invariant that your job will finish not much later than it would have if you got a fair share. So that's the F value. You could set F to 0. If you set F to 0, it just means that no job will ever finish later than it would have in the fair schedule. In this case, that would be 4T for both of these jobs. But given that you have this, you use this slack. You've bought yourself slack. You don't really care about instantaneously being fair. Use this slack to get yourself complementarity between resources to get higher utilization. There's work in progress. We have a bunch of heuristics that for random job mixes try to get you schedules that look more like the one on the right than the one on the left. Again, I'm happy to take questions or chat more. So to summarize, we've told you about 3 things. But the overall idea is that being careful about the resources that you're scheduling gets you better service, better job completion times, better fairness perhaps, but more importantly also higher utilization of your cluster. We've told you how to do schedule construction at the application masters if you have DAGs. If you don't have DAGs, you need not bother about that. And we've told you how to change the task assignment logic in the resource manager that gives you better performance. Bundling, I think, is a cool idea because it lets your scheduler implement complex logic. Like at the end of the day, what's happening with GoodFit is your logic is a bit more complex. You're not just picking the first task, but you want to look a little bit more at the other tasks to see which ones will pack better. If you have to implement this more complex logic without sacrificing the efficiency and the short timeliness budgets of your capacity scheduler or your fair scheduler, you'll need something like bundling. It's a slightly more complex scheduler that gives you the ability to get better assignments while being efficient. And I've told you a little bit about ongoing work. We're thinking of temporarily relaxing fairness and estimating resources and durations for ad hoc jobs you've never seen before. That concludes our talk. We'll be happy to take any questions. Yeah.
So maybe I didn't get it completely, but let's say if there are, so let's say without GoodFit, scheduler is assigning a task T to node A, but is it possible that because of GoodFit, the same task could be assigned to, let's say, node B? So how we are ensuring the locality?
Yeah, sorry. Yeah, so I mentioned that there's certain cases where if you demand that you want your locality not to be relaxed, then we don't actually go through the bundling loop right now. It only works only for relaxed locality equal to true. So there is a flag when you actually ask for a resource whether you want to relax locality or not. If you say I can't relax locality, it doesn't go through the bundling logic right now. I mean, because it doesn't make sense, right? Say I want to go and schedule a task on this node. You can't do any more bundling after that. So. Yeah, obviously. So if you have a bunch of nodes, then you can probably do. But what we do right now is like we don't, for a specific node, if you ask, then you can't. It doesn't go through log. If you have a group of nodes like a node partition or like if you have a rack local kind of thing, then we can still do.
So that's the easy logic.
Yeah.
The slightly more nuanced logic is if you're assigning, if you're missing locality when you're assigning, we lower the score. We have what we call the remote penalty. So this task, assigning a task to a non-local location would not be preferred over assigning some other task on that location that is local. But otherwise, if there are no other tasks, for example, then we would go ahead and do it. It's a penalized score. Remember, we were scoring all the tasks and we were ranking them. As long as we can get these tasks lower scores than otherwise, you could do it. In our clusters, we have some of our clusters are nearly full bisection bandwidth. So rack locality kind of matters, but doesn't matter as much. So this remote penalty, that knob value needs to be tuned. So it depends on yeah, how network intensive your workloads are. Any other questions?
No,
so
with the scheduler load simulator, right? We have done some tests, but we haven't actually published it. Probably like, so once we get the Jira up to date, we'll probably put up some of our stuff also. Sorry? We had initially tried it once for the fast scheduler, but it's not like full-fledged. It's just a random. Not too much to talk about with that.
yeah, SLS we did not do anything. As far, I mean, beyond like initial testing, we did not do. But publicly available datasets, we did a fair bit. So there are 2 papers that are backing this up. One of them is a tech report and a full conference paper. So I encourage you to go look at that. I think in the conference paper, what we did was we ran grid mix workload. We tweaked the workload in order to give us a mix of a configurable mix of CPU, memory, network, and disk dominant workload, and we ran them through on a 200 server cluster, I think it was, and this was the experiments I was showing you before. So I'm happy to make the data that workload available as well. TPC DS, which we ran, was also publicly available.
So there are a couple of business side concerns, such as SLAs and prioritization of tasks. How do you fit those kinds of constraints into this? So in one of the scenarios you talked about long-running tasks, just let them hang out a bit, run a little shorter tasks, but at some point you're going to have to age the task and let it run. How are you going to capture all those business side requirements into this?
Yeah, that's a great question. I think Arun alluded to this a little bit. Remember his statements about how he dealt with the application master, the job manager. Those would be similar to your concerns about doing any higher priority allocations. So higher priority allocations get effectively a fast pass through the scheduling loop. So they get allocated with a shorter latency. They get preemptible. I mean, they jump to the head of the queue basically.
Right. Some SLAs, for example, might be 6 hours, but if you keep postponing it, you reach the 6-hour boundary and all of a sudden.
Right, right. So the way that gets handled today in Yarn is reservation logic. So if a task is at the head of the queue and keeps, for whatever reason, not getting allocated for say some n times, it gets dibs on the next machine that's going to come up.
That's the aging factor, right?
Correct, correct. So we respect aging exactly as it is. In addition to, while we are bundling, we respect aging. So aging logic works as before in spite of bundling. But there are other business policies like SLAs. I don't think they're, I mean, they're better, more capable committers up here. They can say better about this. But SLAs, I don't think there's any explicit support. So once there is, I think you can incorporate that in addition to our bundling stuff.
So you're talking about SLAs for allocate SLAs. So
Well, so a lot of times what customers will do is they will say, I will take my schedulers and I will assign queues so that jobs with tighter SLAs will get a higher priority based on the fact that
okay.
in the queue they can steal more resources and things like that. And that's how they try to manage it as a way of saying, I have this business need for whatever minutes or hours or whatever it is that we happen to be doing. And so for many clients, they're not seeing, the secondary concern is how
Okay.
it's packed and how efficient it is. They tend to look at it more from the perspective of, I need my job, I need my results in this period of time.
Yeah, but that is kind of orthogonal to this specific
Right, but
thing, right?
it
Yeah.
results in how the jobs are packed. So I used to work for a different company where we were looking at per minute how many thousands of jobs were being executed
Okay.
That's great. But in the end, you do have to have a result in a certain period of time for some cases.
Yeah. I hear you. I think
More like what you said. I mean, you can
Yeah.
use heuristics and run times and all to go and take that as an input for a packing. Kind of
Yeah.
thing, yeah.
So there's some simple heuristics that get you such SLAs like EDF. If you're trying to do earliest deadline first, then earliest deadline first is implementable in conjunction with this one, and you could get it just right. But there are more complex logic, such as something is a little bit more time elastic or periodic, and you could push the time elastic stuff into the valleys that you anticipate. So that kind of stuff requires a little bit more careful planning. Yeah. So for these more careful planning, I think our sister team has work. It's called Rayon.
Yeah. That reservation.
So it's a lot more complex actually. There's a plan follower and a leader who kind of imagines what the cluster might be, say next hour or next couple of hours, and then kind of tries to say give you like a longer term share or a reservation of the cluster, so that you fit the overall plan. So it's kind of like a meta scheduler that kind of looks further into time. I would encourage you to look into that as well.
It's there actually in Hadoop. It's been shipping from 2.6 onwards. It's called the Reservation API for deadline tasks. Yeah.
Any more questions?
So, for several reasons, configurations do global scheduling. So today it's all reactive and driven by node heartbeats, right? And there are a few reasons why people are considering switching it from reactive and node based to a global thing. How do you see doing GoodFit in the context of that? Because you're not assigning for a node anymore, so that you can pack on the node. You're basically assigning for all the nodes at once. And in that case, like how much would alignment, I guess, would still make sense, but like how does the bundling cost amortize over time?
Yeah, that's a great question. So when you say global scheduler, right, it's there's a lot going on. I mean, at some level, you could argue that your RM is already a global scheduler, because it already has some global state of the cluster. At least it knows all the pending tasks, and it is using all of that information to go in. I think what you have in mind is a scheduler that's not just aware of all the pending tasks or pending container requests, but is also aware of say future state of the machines, so that it's doing look ahead allocation, so that upon node heartbeat the containers are already available or something. It's like my first order thought is that bundling would just apply even over there. I would apply it with bounded look ahead. I wouldn't pack things way too further into the future, just because you don't know which tasks will, tasks might fail and you want to give yourself some room. So I don't want to allocate too far into the future, but I can do look ahead, say a couple task durations, and we would do bundling for a couple task durations ahead right away. Would be what I would aim for. But we have to chat a little bit at length to see what you really have in mind. Like if you could give us, here's the code flow without bundling, I'm pretty confident we could give you a code flow that captures all of that and bundles. Any final question? Cool. Thanks for coming.
Yeah.
Yeah. Hope you have a great time.